There is a number that describes the universe you live in, and it is stranger than almost anything else in science. 70%. 70% of everything that exists, every joule of energy, every ounce of substance, every quiet unit of the cosmos, belongs to something we cannot see, cannot touch, and cannot fully explain. It has a name. We call it dark energy. But the name is almost an apology, a placeholder for an answer we have not yet earned. And here is the part that should sit with you for a long moment. This invisible majority is not passive. It is not simply present. It is active. It is pushing. And that pushing is the reason the space between every galaxy in the sky is widening right now as you listen to this sentence. Think for a moment about the version of the universe most of us carry in our heads without ever examining it. Gravity pulls things together. Stars pull in gas and dust. Galaxies pull on each other, drift closer, sometimes collide. On the largest scales, we assume gravity should be the only real author of cosmic history. A slow, patient hand drawing everything inward, or at the very least, slowing whatever expansion happened at the beginning. That assumption feels safe. It matches what we see falling apples do, what we see moons do, what we see stars do. It is intuitive, and it is wrong. Because the actual universe is not slowing down. It is accelerating outward. And it has been for billions of years. And the force responsible for that acceleration outweighs every star, every planet, every black hole, every trace of ordinary matter combined. We are not living in a universe that is coasting to a gentle stop. We are living in one being pushed apart by something with no shape, no particle, no location. Something that seems to be a property of space itself. That is the paradox at the heart of tonight's dark archive. The emptiest thing we know how to imagine is also the most powerful thing in existence. And if you can sit with that contradiction, if you can let it feel less like an error and more like an invitation, then what follows may change the way you picture the sky forever. If this is your first time here, welcome. Get comfortable, settle in, and if the channel's way of exploring these questions resonates with you, consider subscribing. Not because the video needs it, but because there is a long, quiet road of these questions still ahead of us, and it helps to walk it together. Tonight, we are going to follow this particular question as far as it will take us. What is dark energy really? And what does its existence tell us about the fate of everything? Let's begin where most of us actually live our lives. Not among galaxies, but among ordinary things. Imagine releasing a ball in the air. It rises, slows, and falls back down because gravity is patiently reeling it in. Imagine two people standing at opposite ends of a large, quiet room, both slowly walking toward the center, drawn there by nothing more than the shape of the space they share. This is the entire logic of gravity as most of us understand it intuitively. Things that have mass are attracted to other things that have mass, and given time, they move closer together, not further apart. Now, scale that same intuition up. Take the whole observable universe. Every galaxy, every star, every cloud of hydrogen drifting in the dark, and ask what should happen to it over billions of years if gravity is the only major force at work. The prediction is simple and it is elegant. Expansion should slow. The outward motion left over from the universe's earliest moments should gradually lose momentum, the way a ball thrown upward loses its climb, dragged down by the combined gravity of everything else in existence. Cosmologists spent much of the 20th century assuming exactly this. The open question was never whether the universe was slowing. That felt obvious. The open question was only how much. Would gravity be strong enough to eventually halt the expansion and pull everything back into a final collapse, a mirror image of the Big Bang running in reverse? Or would there simply be too little matter, allowing expansion to continue forever, but always decelerating, always losing speed, like a rocket escaping a planet's gravity well with just enough fuel to coast on forever, but never fast enough to feel free of that gravity's grip completely? That was the frame. That was the entire debate. Two possible endings, both governed by the same trusted force, both variations on the same theme. Gravity wins, eventually, in one direction or another. But here is where the intuition begins to fail. And it fails in a way that no one predicted. Because in the late 1990s, two independent teams of astronomers set out to measure exactly how much the expansion of the universe was slowing down. They used a very specific kind of exploding star called a Type Ia supernova, a stellar detonation so consistent in brightness that astronomers use it as a kind of cosmic ruler, a way of measuring almost unimaginable distances by comparing how bright these explosions appear from Earth to how bright we know they actually are. The method is elegant in its simplicity. If you know how much light something truly gives off, and you know how much of that light reaches you, you can calculate exactly how far away it is and how long its light has been traveling to reach your eyes. The astronomers measured dozens of these ancient explosions, some so distant that their light left home before our solar system had even finished forming. And the goal was to trace the history of cosmic expansion by watching how these supernovae had moved over billions of years. It should have been an exercise in confirming what everyone already believed. It became one of the most quietly shocking moments in modern astronomy. The supernovae were dimmer than expected. Not brighter, dimmer. And dimmer means farther away than a slowing, decelerating universe would allow. Every model, every calculation, every reasonable expectation pointed to a straightforward conclusion. The expansion of the universe is not decelerating at all. It is accelerating. And it has been accelerating for roughly the last 5 billion years. A window of cosmic time larger than the entire age of our own solar system. This is the part that deserves to be said slowly, because it can be easy to let the strangeness slide past unnoticed. The force pulling galaxies together, gravity, should have been slowing the expansion down, the way friction slows a rolling ball. Instead, something else was speeding it up. Not slightly, not as a rounding error in the data, consistently, and by an amount too large to be a mistake, too large to be explained by gravity behaving in some unexpected way, too large to be explained by anything already sitting comfortably inside the physics textbooks of the time. Two teams, working independently, competing for the same discovery, arrived at the same astonishing answer. The universe was not just expanding, it was expanding faster with each passing era. And whatever was causing that acceleration had to be powerful enough to overwhelm the combined gravitational pull of every galaxy, every star, every strand of the cosmic web, all at once, across the largest scales that exist. This is the moment the phrase dark energy entered the language of physics, not as an explanation, but as a name for the gap in the explanation, a placeholder for whatever it is that behaves like a kind of pressure built into space itself, one that pushes outward rather than pulling inward, and one that appears to be gaining strength relative to everything else in the universe as that universe grows larger and more diffuse. But this is still only the surface of the mystery, because naming a force is not the same as understanding it, and what dark energy actually is, physically, remains one of the most open, most contested questions at the frontier of modern cosmology. To understand why dark energy is so strange, it helps to understand what physicists thought empty space actually was before this discovery forced a reconsideration. For most of scientific history, the vacuum of space was assumed to be exactly what the name implies. Nothing. An absence, a stage on which matter and energy perform. Quantum physics complicated that picture decades before dark energy was ever detected, revealing that so-called empty space is anything but calm at the smallest scales. Quantum field theory predicts that even a perfect vacuum seethes with brief, fleeting fluctuations. Particles and their antiparticle counterparts This is not speculation. These vacuum fluctuations have measurable, verified consequences in laboratory experiments, subtly nudging the behavior of atoms in ways physicists have confirmed again and again. So there was already a reason to suspect that empty space might carry some form of intrinsic energy. The trouble is a matter of scale, and it is a problem so severe that if the vacuum truly contained the energy that quantum theory predicts, the universe would have This is one of the strangest coincidences in physics. There is a name for this observed value when treated as a fixed property of space: the cosmological constant. It was actually proposed by Einstein himself decades before dark energy was discovered, though for very different reasons. When Einstein first worked out the equations of general relativity, he realized they predicted a universe that could not remain static. It had to be either expanding or contracting, never perfectly still.
At the time, the prevailing assumption was that the universe was fixed and eternal, so Einstein inserted an additional term into his equations, a kind of built-in repulsive
pressure, specifically to balance gravity's
attractive pull,
hold the universe in a state of equilibrium. Later confirmed that the universe actually was expanding, Einstein removed the term, reportedly calling it the biggest blunder of his career.
But here is where the story bends back on itself in a way that feels almost too poetic to be true. Decades later, when astronomers discovered that the expansion of the universe was accelerating, the mathematics of Einstein's abandoned term turned out to describe the observed behavior with remarkable precision. The very concept he had discarded as an embarrassing mistake may, in fact, be one of the most accurate descriptions we have of the dominant force shaping the universe's future. Not because Einstein was right about why he needed it, but because the mathematical shape of the solution had been sitting in his equations all along, waiting for the observation that would give it meaning.
This is the part that tends to quietly astonish people once they sit with it. We are not talking about a force with a source, the way gravity has mass as its source, or electromagnetism has charge. Dark energy appears to be a property of space itself, meaning that as the universe expands and creates more space, it does not dilute dark energy the way expansion dilutes matter and radiation. It creates more of it.
More space means more dark energy, which drives more expansion, which creates still more space. It is less like a force pulling on already existing space, and more like an intrinsic feature woven into the geometry of the vacuum, one that scales with the size of the universe, rather than being spread thin across it.
But this explanation, elegant as it sounds, is only one candidate among several, and none of them has been confirmed beyond reasonable doubt. And that is where the mystery deepens rather than resolves. But to understand what deepening actually means, we need to widen our view from the vacuum of individual space to the largest structure science has ever attempted to measure, the observable universe as a whole, unfolding across billions of years. This brings us to one of the central open questions in physics today, and it deserves the kind of careful, honest framing that separates confirmed fact from active hypothesis, because both exist within this story, tangled together. But roughly 5 to 6 billion years ago, something shifted. As the universe expanded, the density of matter within it thinned out, spread across more and more volume, growing ever more dilute. Dark energy, by contrast, did not thin out in the same way. If it truly is a property of space itself, then as space grows, the total amount of dark energy grows with it, while the amount of matter stays fixed and simply spreads thinner across a larger volume. There came a moment, a genuine turning point in cosmic history, when the outward push of dark energy overtook the inward pull of gravity from all that ordinary and dark matter combined. Before that moment, expansion was decelerating, exactly as classical intuition would predict. After that moment, expansion began to accelerate, and it has continued accelerating ever since. We happen to be observing the universe during this specific transitional era, a universe in which dark energy has only recently, in cosmic terms, become the dominant force shaping its large-scale behavior. Look far enough away, and therefore far enough back in time, and you are looking at a younger universe, still governed primarily by gravity's slow, patient inward pull. Look at the more recent universe, the one we and our galaxy actually inhabit today, and you are looking at a cosmos being steadily, silently pushed apart. This changes the meaning of looking at a distant galaxy. The light reaching your eyes tonight, if you were to look up, could have left its source at a moment when the universe itself was still decelerating, when the very physics governing the expansion of space was fundamentally different from the physics governing it now. Every photograph of a distant galaxy is, in a very real sense, a photograph of the universe operating under different rules than the ones shaping its present. And here is where the anomaly deepens further, because dark energy is not simply reshaping the future of individual galaxies, it is reshaping the future of causality itself on a cosmic scale. Consider a galaxy sitting at the very edge of what we can currently observe, its light having traveled toward us for the better part of the universe's entire history. Because space itself is expanding, and because that expansion is accelerating, there will eventually come a point, a real physical point in future cosmic time, beyond which the light from that galaxy and countless others will never reach us. Not because the galaxy moves away faster than light travels through space, which would violate nothing since it is space itself doing the stretching rather than any object moving through it, but because the space between us and that galaxy will be expanding fast enough that any light it emits from that point onward will never be able to close the growing distance. That galaxy will not disappear. It will simply become permanently, physically unreachable, cut off from us, not by distance alone, but by an accelerating gulf of space that grows faster than light can cross it.
this is not a distant, uncertain speculation. Based on current measurements of dark energy's strength, astronomers calculate that this is already happening to some of the most distant galaxies we can see, and it will continue happening to progressively closer galaxies as the eons pass. A future observer, standing where we stand today but living tens of billions of years from now, would look up and see far fewer galaxies than we do. Not because those galaxies had been destroyed, but because they will have been carried beyond the reach of any signal, light included, that could ever cross the ever-widening gulf between here and there. Here is the layer where intuition tends to fail completely. So let's slow all the way down. We're used to imagining the universe as a fixed stage on which objects move. Objects can approach each other, objects can retreat from each other, but the stage itself, the space in between, is assumed to simply exist, static and unchanging, an empty backdrop rather than an active participant. Dark energy reveals that assumption to be false.
Space is not a backdrop. Space is not passive. Space has, apparently, a form of internal pressure, an active tendency to stretch. And that tendency does not weaken as space grows larger. If anything, its total effect strengthens, because there is simply more space in which it can act. The error, in other words, is imagining an accelerating universe the way we imagine an accelerating car, as an object receiving a force from outside itself, being pushed along a track that already exists. But there is no track. There is no outside. The acceleration is happening within the very fabric that would normally be considered the track itself. Space is stretching, and it is stretching because of a property that appears to belong to space, not to anything moving through it. This brings us to one of the central open questions in physics today, and it deserves the kind of careful, honest framing that separates confirmed fact from active hypothesis, because both exist within this story, tangled together. What we know with a very high degree of observational confidence is this: the expansion of the universe is accelerating, and has been for roughly the past 5 to 6 billion years. This has been confirmed not only through supernova observations, but through multiple independent lines of evidence, including detailed measurements of the cosmic microwave background, the ancient afterglow of the universe's earliest light, and through large-scale surveys mapping the distribution of galaxies across billions of light years. These independent methods converge on a consistent picture. Roughly 70% of the total energy content of the universe exists in this form we call dark energy, with the remainder split between dark matter and the ordinary matter that makes up stars, planets, and everything we can directly touch and see. What we do not know with anywhere near the same confidence is what dark energy actually is at a fundamental level. The leading hypothesis, favored by many cosmologists for its mathematical simplicity, treats dark energy as the cosmological constant we discussed earlier, a fixed, unchanging property of space itself, with a constant density that never varies across cosmic history or physical location. This model fits the vast majority of current observational data extremely well, which is precisely why it forms the backbone of the standard cosmological framework most astronomers use today. But fitting the data well is not the same as being confirmed as physically true. And the enormous mismatch between the predicted vacuum energy from quantum field theory and the tiny observed value remains, by any honest account, unresolved. An alternative hypothesis proposes that dark energy might not be constant at all, but instead a dynamic field that changes in strength over cosmic time, sometimes referred to as quintessence. Under this framework, the push of dark energy could theoretically strengthen, weaken, or even reverse across the deep future, depending on the specific behavior of whatever underlying field is responsible.
some recent large-scale survey data, still being analyzed, still being debated, still very much a live area of research rather than settled consensus, has hinted, though not confirmed, that dark energy strength might not be perfectly constant after all. A finding that, if it holds up under further scrutiny, would represent a genuinely significant shift in how physicists understand the driving force behind cosmic acceleration. A third possibility, more radical still, suggests that there may be no dark energy at all, in the sense of an actual substance or field. That what we are observing might instead be a sign that our understanding of gravity itself breaks down at the very largest cosmic scales, requiring a modification of general relativity rather than the introduction of a new form of energy. This approach has struggled to match the full breadth of observational evidence as successfully as the Standard Model does, but it remains an active area of theoretical research, not a fully discarded idea. It is important to say clearly, these are not settled facts competing with wild speculation. They are genuine, actively researched hypotheses, each with real theoretical motivation, each facing real observational challenges, and each still capable of being right. This is what the frontier of physics actually looks like. Not a single confident answer waiting to be revealed, but multiple careful, mathematically rigorous possibilities, narrowing slowly as better instruments and larger surveys gather more precise data with each passing year. But the answer to this question is not simply an academic curiosity. It reaches directly into the deepest question any of us can ask about the universe we live in. How does this end? To understand why dark energy matters so profoundly for the universe's future, it helps to bring in one of the oldest and most fundamental principles in all of physics, entropy, and the second law of thermodynamics. The second law states, in its simplest form, that in any closed system, disorder tends to increase over time. Energy disperses. Concentrated, useful forms of energy, the kind capable of doing work, of driving processes, of powering stars, tend to spread out into diffuse, unusable forms, most commonly low-grade heat, evenly distributed and no longer capable of driving further change.
This is why a hot cup of coffee cools to match the temperature of the room around it, and never the other way around. This is why a star burns through its fuel and eventually fades, rather than spontaneously regathering its scattered light back into a single concentrated source. The universe, considered as a whole, appears to be a closed system obeying the same relentless principle, and it has been doing so since the earliest fractions of a second after the Big Bang.
Ordinarily, entropy and gravity exist in a kind of long, slow tension. Gravity pulls matter into concentrated, orderly structures, stars, galaxies, planets, which looks on the surface like a decrease in disorder. But this apparent order comes at a cost. The process of gravitational collapse itself releases enormous amounts of energy as heat and radiation, ultimately increasing the total disorder of the universe by a far greater amount than the local order it creates. Stars are, in this sense, engines for producing entropy, converting the ordered potential energy of gravity into the disordered chaos of starlight, spread outward across the cosmos.
Dark energy interacts with this principle in an entirely new way, one that previous generations of cosmologists never had to seriously consider, because previous generations assumed gravity alone would eventually reverse cosmic expansion, pulling everything back together into a hot, dense state, not unlike the one the universe began in, a scenario sometimes called the Big Crunch.
In that scenario, entropy would still increase throughout the process, but the geometry of space itself would eventually collapse, bringing everything back into contact, everything back into potential interaction, before some final, catastrophic contraction. Accelerating expansion, driven by dark energy, closes off that possibility entirely. If the acceleration continues indefinitely, as the standard cosmological model currently predicts, there will be no eventual reversal, no final contraction, no big crunch. Instead, space will continue stretching faster and faster, pulling galaxies apart over spans of time almost impossible to render meaningful in human terms. Not millions of years, not billions of years, but numbers that require entirely different vocabulary to even approach. Stars will exhaust their fuel and go dark, one by one, with no new stars forming to replace them, because the raw material for star formation will itself have been stretched too thin, spread across too vast a volume to ever collapse into new stellar nurseries again.
This is the scenario physicists refer to, somewhat starkly, as heat death, or the era of maximum entropy, a future universe in which energy has become so thoroughly and evenly diffused that no meaningful work, no meaningful process, no meaningful change of any kind can occur. Not an explosive ending, not a dramatic collapse, simply an ever-expanding silence, growing colder, growing darker, growing emptier for what may effectively be an eternity. It is worth pausing here to notice something almost unbearably strange. The same force responsible for the vibrant, structured, star-filled universe we currently observe, the same category of force whose earliest inflationary cousin may have stretched an unimaginably tiny region of the infant universe into the vast cosmos we inhabit, may also be the very same category of force responsible for erasing all of that structure again, slowly, patiently, over timescales that dwarf everything that has happened since the Big Bang combined. Creation and dissolution, in this framing, are not opposites. They may be two expressions of the exact same underlying property of space.
And yet, here is where honesty about the frontier of research becomes essential once again. This heat death scenario, as dominant as it currently is within cosmology, remains a projection built from our best current understanding of dark energy's behavior, not a guaranteed, unavoidable outcome. Everything about this fate depends entirely on one crucial, unresolved detail: whether dark energy strength genuinely remains constant across the deep future, exactly as the cosmological constant model assumes, or whether it changes in ways current instruments are only just beginning to have the sensitivity to detect. If dark energy is not perfectly constant, but instead slowly weakens over cosmic time, the outward acceleration we currently observe could eventually slow, potentially allowing gravity to reassert some influence over structures that have not yet been pulled entirely beyond its reach. If dark energy instead strengthens over time, a far more extreme possibility opens up, one cosmologists call the Big Rip, a future in which the acceleration of expansion grows so extreme that it eventually overcomes not just the gravity holding galaxies together, but the gravity holding solar systems together, then the electromagnetic forces holding planets and stars together, then eventually the nuclear forces holding atoms themselves together, tearing apart every bound structure in the universe, down to the smallest scale, in a finite and calculable amount of time. These are not equally likely outcomes competing on equal footing. Current data still favors the simpler, constant cosmological constant model, and the Big Rip in particular requires a very specific and currently unsupported set of assumptions about dark energy's behavior. But the honest scientific position is that we do not yet have enough precision in our measurements to rule out every alternative with total confidence. Ongoing and upcoming large-scale sky surveys, designed specifically to map the distribution and behavior of galaxies across enormous stretches of cosmic time, are actively working to narrow these possibilities further, refining our picture of dark energy's true nature with each new dataset they produce. What remains genuinely, deeply unresolved is not whether dark energy exists. That has been confirmed through multiple independent methods, converging on the same conclusion. But what dark energy fundamentally is, at the level of underlying physical law? Is it a true constant, woven permanently into the fabric of space-time, unchanging for the remainder of cosmic history? Is it a dynamic field, still evolving, still capable of surprising us in the coming decades as new data arrives? Or is it perhaps not a form of energy at all, but a signal that our equations for gravity itself require revision on the largest scales? A limitation not in the universe, but in the theoretical tools we have used to describe it. Each of these possibilities remains, as of the most current research, a live hypothesis rather than a settled fact. And that uncertainty, rather than being a weakness in our understanding, is precisely what makes this one of the most active, most closely watched frontiers in all of physics today. Return for a moment to the question that opened this exploration. What is dark energy? And what does it mean that the majority of everything that exists is something we cannot see, cannot touch, and cannot yet fully explain? The question feels different now than it did at the beginning, and it should. What began as a puzzle about a mysterious, invisible substance has become something There is something worth holding on to in this, even amid the vastness of the timescales involved. Every galaxy you have ever... Perhaps that is the real lesson tucked inside 70% of everything. That understanding a universe means accepting that some of its most powerful forces will remain, for a while longer, the least understood. Dark energy does not announce itself. It has no particle we have caught, no signal we have decoded, no laboratory experiment that has isolated it directly. And yet, its fingerprints are written across the accelerating gulf between every galaxy in the sky, in the light of supernovae that traveled billions of years to tell us a story about a universe that refuses to slow down. The question we began with was simple. What is pushing everything apart? The answer we are left with is larger, stranger, and far from finished. And perhaps that is exactly the shape a true frontier of science should take.